Hello, back at it again. It's been about 10 minutes since I did the last video. Time to do another one while I'm feeling up to it. Okay, question one. And by the way, got to do the little intro. This is the midterm 1 material section of the spring 2018 final for MA266. So let's do it. Question one, let's find the solution to this initial value problem given here. Okay, so we see that dy dx is equal to some function of x over some function of y. So let's multiply that some function of y over to the left side, 2y minus 6. And then let's multiply dx over to the other side is equal to 4x cubed plus 1 dx. We can integrate both sides. We will get y squared minus 6y is equal to x cubed. By cubed, I mean fourth plus x plus c. So at this point, let's apply our initial condition here. Y at 1 equals 2, so 4 minus 12 is equal to 1 plus 1 plus c. This is negative 8. This is 2. So overall c is negative 10. If c is negative 10, we can rewrite this as y squared minus 6y is equal to x to the fourth plus x minus 10. And it might be a little unclear from this point how we're going to get things into an explicit form for y equals, but and I'm not joking. I figured this out 5 minutes ago. We can complete the square. So if we add 9 to both sides, which is completely legal to do, we will get y squared minus 6y plus 9 is equal to x to the fourth plus x minus 1. This will become y minus 3 quantity squared is equal to x to the fourth plus x minus 1. We can square root both sides and add 3, and y is equal to 3 plus or minus the square root of x to the fourth plus x minus 1. And we have to make sure that we use the correct plus or minus side. So when we plug in x equals 1, we want to get 2 out. So y is equal to 3 minus the square root of 2 minus 1. So the square root of 1. And so we're going to need that negative side. Can't have both. So A is our correct answer for number 1. 2, let y of t be an exact solution of the following initial value problem, and let y app of t be the approximate solution of this initial value problem using Euler's method with a step size h equals 1, and we're looking for yap of 3. So our first condition, y of 1 is equal to 0, is where we're going to start off. We see that y prime is actually not isolated up here. So let's get that figured out. Y prime minus 2 over t, y is equal to 1. Okay, that's helpful. So we see that y prime is equal to 2 over ty plus 1. So we can use this initial condition, y at 1 equals 0, to start plugging things in to figure out our solution. And in general, the equation for the next approximation, so y at n plus 1 is equal to y at n plus h, our step size, times y prime evaluated at n. So let's do this. So y at 2, because our initial condition is at 1 and we're moving by steps of 1, is approximately y at n, so y at 1, which is 0, plus h, our step size, which is 1, times y prime at 1, 0, which will be 2 over 1 times 0 plus 1, which is just equal to 1. So we have a new condition to work with. That is y at 2 is equal to 1. That lets us approximate y at 3 in exactly the same way. That's going to be equal to y at 2, which was 1, plus our step size, which is 1, I won't even write it out, times 2 over t. Our t value for our previous step was 2, times our y value for our previous step, which was 1, plus 1, and that's equal to 1 plus 2, or 3. So 2 is C. 3. What's the largest open interval in which the solution to this initial value problem is guaranteed to exist by the existence and uniqueness theorem? So we're guaranteed to have a solution to an initial value problem like this when our equation is in the form y prime plus p of x, in this case it's t, p of t, y plus or is equal to q of t. And that means that we have to isolate our y prime. So let's divide everything by t squared. We will get y prime plus ln quantity t minus 1 over t squared e to the t minus 2 times y is equal to t minus 5 divided by sine t minus 4 times t squared. So we'll see pretty quickly that q of t, given right here, or sorry, p of t given right here, and q of t given right there, are undefined when t is equal to 0, or when t is equal to any multiple of 4 plus pi. Yes, so yeah, 4 or t equals 4 plus pi, t equals 4 minus pi. And that's coming from our sine term here. Any time that what we're plugging in there is a multiple of pi, we'll have a bad time. Also, we don't just need to look at our denominator, because in our numerator over here we have ln t minus 1. So that is undefined for t less than or equal to 1. So looking at our initial condition, y at 3 is equal to pi, we're looking for the largest rectangle, so 3, the largest rectangle that we can draw around 3 without hitting any of these no good values. So 4 minus pi is less than 1. So the first condition that we run into on the left-hand side is 1, and the first condition that we run into on the right-hand side is 4. And so given that our solution runs through or begins at 3, we can only guarantee that a solution exists between 1 and 4. So D is our correct answer for C. I mean 3. Question 4, let's identify the differential equation that corresponds to the direction field on the right. So we see that -2, if I draw out the arrows where the slope is going, in this case, we see that the field is flowing up towards y is equal to -2. From 0, it's flowing down to y is equal to -2, and it is flowing up from 0 up to infinity. So we are looking for an equation where 0 is an unstable point and 2 is a stable point. And I'm not going to walk you through all of the terrible not guessing and checking, but there is a lot of guessing and looking through all these options to see that we get all this behavior. But if we take a look at option C, we'll see that that for y is equal to -1, we are going to get negative 1 plus 2 over negative 2. So that gives us the negative value we want to see there. If we choose negative 3, we will get negative 1 over some other negative number. So that gives us that positive number that we want for that section. And anything above 0, let's say 1, we will get our positive value. And you can also kind of see this behavior where when we're dividing by 0, or as y approaches 0, our from either direction, our slope approaches infinity and negative infinity from either side. And I'm pretty sure that there's one of these other answer choices that acts very similarly, but you know, it's harder to see. It's harder to see that behavior. Okay, so 4 is C. Let's solve the initial value problem for this homogeneous equation here. Right off the bat, we're going to be using the substitution y over x is equal to v. And that's just something, if you see this kind of form enough, that will just pop into your mind. And we know that dv dx times x plus v is equal to y prime. So we can make that substitution. dv dx x plus v, where this is multiplied in there, I want to make that clear, is equal to, okay, let's divide all of the terms in our right-hand side by x to the 4th. We get 1 plus v to the 4th divided by v cubed. We'll subtract the v over minus v, and in order to multiply this in, we'll have to multiply it by v cubed over v cubed. So this will be minus v to the 4th over v cubed. And so these two will cancel out. We're left with 1 over v cubed. Let's see, we can divide both sides by dv, and I'll just make this clear, x over dx. And let's take both sides to the negative 1 power, and we can integrate. The integral of 1 over x dx is equal to the integral of v cubed dv. And just flipping things back around, this will give us v to the 4th over 4 equals ln x plus c. Multiplying both sides by 4 and taking our root, we are going to get v is equal to the 4th root, so ln x, 4 ln x plus c to the 1/4 power. We can replace this with y over x and multiply our x over like so. And we see that the only answer choice, even vaguely in this form, is option C. But if we apply y at e equals e, this will be y equals e times the 4th root of y is equal to e. So e equals e times, well, whatever's in here has to be 1. 4 ln e is just 4 plus c, so c has to be negative 3 in order for that to evaluate to 1. So 5 is C. 6, let's find the solutions of this guy right here. Let's divide everything by 2t, get y prime by itself, minus 2 over t y is equal to 3t cubed, and by 3 I mean 2t cubed, e to the t squared. So we're going to be applying the integrating factor method here. So we're taking e to the integral of negative 2 over t dt, where that's this p of x function in here, and we're setting this equal to rho of x. And you know, we can simplify this down. We've done this many times. This is t to the negative 2. So we know that y of t is going to be 1 over t to the negative 2, or t squared, times the integral of t squared, of rho here, multiplied by q. So that will give us 2t e to the t squared dt, where this integral will evaluate to e to the t squared e to the t squared plus c. Now all we have to do is apply our initial condition. 0 equals 1 e to the 1 plus something. Well, in order for this to evaluate to 0, this would have to be minus e. So c is minus e. And expanding this out, we would get y of t is equal to t squared e to the t squared minus e t squared. And so our answer choice, our correct answer for 6 is A. Okay, 7. Big polynomial alert whenever we see anything this huge, and especially if we have answer choices with 1, 2, 3, 4, 5, and technically 6 polynomial terms, we should have a good idea that this is going to be an exact equation. So if we take this term here, and we call that m, and we take this term and call it x, if my is equal to n, oh my god, I did that twice in a row. If this is equal to nx, I kept calling that one x. If these two are equal, then both of these functions are partial derivatives of the same overall function. So my is going to give us 6x plus 2y, and nx is going to give us 6x plus 2y. Would you look at that? So this is an exact equation. All we have to do is integrate m dx. So integral of m dx will give us 3x squared y plus x y squared. And then on the other side, the integral of n dy will give us n dy 3x squared y plus xy squared plus y squared. And so since we only count the overlap between these once, you can go kind of remind yourself why this is if this doesn't make sense to you with the potential function stuff that we saw back in Calc 2. We can combine these. We see that there's overlap here and overlap here, so we'll only count each of those ones, and we will get 3x squared y plus x y squared plus y squared being equal to c. And so just based on that, we can choose our answer. And if you really want to prove to yourself why we don't double count these things that we've integrated for, take this guy and find its partial derivatives, and you'll see that you get two copies. So this 3x squared y term will turn into both 6xy and 3x squared. But when we integrate back up to find it, we don't want to double it. Okay, so applying this initial value here, y at 1 equals 3, we will get 9 plus 9 plus 9, or 27. So 7 is clearly E. 8, let's consider this initial value problem given here. What is the initial value y? For what initial value y0 is the limit as t approaches infinity of y of t1? So essentially they're asking about the stability of these different roots, where our roots are y equals 0, 1 with a multiplicity of 2, and 2. So we can set that up 0, extending on down, 1, 2, and extending up to infinity. And I'll make that a little bit longer there. So we're looking for which side of 1, either between 0 and 1 or 2 and 1, which side of that leads back down to 1 as we approach t equals infinity. And so all we have to do is plug in some values. So if we plug in 1.5, we will get negative 1.5, 1.5 minus 1 squared, 1.5 minus 2. And we see that this will give us a positive term here, a negative term here, and a negative term here. So our result is a positive slope for that area. but by that area I mean this interval on y. What about between 0 and 1? Well, if we plug in 0.1, we are going to get negative 0.1 times 0.1 minus 1 squared times 0.1 minus 2. And this is a negative number times a positive number times a negative number, aka a positive number. So if we choose the value 0.001, eventually, as t approaches infinity, we will tend up towards 1. So 8, our answer is B, which is correct. Let's suppose that u of t, it's given there, is a solution to a mass spring system. The period and amplitude of u of t are. So it's a little bit of a silly way that I'm using to solve it. It's definitely not rigorous, but I just noticed this looking through it. We've barely learned this topic in class, so I'm definitely not too comfortable with it. But we can look at this. So the period of this system is 2 pi divided by whatever we have in here. So 2 pi over 3. That already narrows it down to 3 options, and then I'm not sure if there's any rigor behind what I'm about to do, but I noticed that these two here, our coefficients out here, form a Pythagorean triple with 5, aka 3 squared plus 4 squared equals 5 squared. No clue if that has anything to do with why 5 is the solution, but 11, as it turns out, is C. So go figure. So don't take anything that I just did there besides the period. I do know that calculation of the period was correct, but don't try not to take that too seriously. 12. Okay, back in something that we know how to do. The function y1 equals t to the negative 1 is a solution of that equation right there, and we are looking for the second solution. Well, we're not looking for the entire second solution. We're looking for the portion of the second solution multiplied by the second solution to give us that second solution. That's a lot of solutions. By reduction of order. So we're doing this using reduction of order. And the first thing that we want to do is isolate y double prime. So y double prime plus 3 over t y prime plus 1 over t squared y is equal to 0. And we have a nice equation for reduction of order in general. That's y2 of t is equal to y1 of t times one really big integral of e to the negative integral of p of t dt over y1 of t quantity squared dt. So p of t in our case is this value over here. Remember, we always call this p and this guy q in these second order cases. So we have minus 3 over t dt. This integral will give us 3 ln t. Oh my god. God damn it. I'm sorry about that. I'm going to leave it in there just to annoy you guys. So e to the negative 3 ln t is going to give us t to the negative third. And y1 we can replace with our first solution, which is just t to the negative 1. So 1 over t, and this will be 1 over t squared. And rearranging things, this guy will go up top, and this guy will go down at the bottom, and we can cancel those guys out. So y2 of t is equal to 1 over t times ln t plus c. And since they're looking for v of t, which is the component that's multiplied by 1 over t, then v of t could be ln t if c is equal to 0. So 12 for 12, our answer. Our answer is B.